Suppose a young girl is about to learn bicycling. If she practices on her own, it would be dangerous, and she will likely fall and hurt herself. Instead, if her father guides and protects her by hand and gradually lets go as her skill progresses, she will learn bicycling much more smoothly. Now, imagine a humanoid robot. It is way too dangerous to let it learn locomotion skills on its own in the real world. You may think that we can use sim-to-real RL and domain randomization to deploy a pre-trained policy directly. However, the systematic sim-to-real gap cannot be fully closed, and optimal real-world performance can only be achieved by direct real-world learning. Inspired by the human approach, we propose using a robot arm as a teacher to hold the humanoid and an adaptive treadmill to keep the robot within the arm's reaching range. A 6DUF force-torque sensor is mounted at the end of the arm to provide feedback control signals and real-world RL rewards. We present Robot Trains Robot, or RTR, a holistic system of hardware and algorithm innovations to support real-world humanoid learning. During real-world training, the robot arm can move horizontally to follow the humanoid, giving it safe and sufficient freedom for exploration, or it can perturb the humanoid to improve its robustness. The arm can also adjust vertically to provide a curriculum of supporting forces, and it can reset the robot automatically when it falls, minimizing the need for human intervention. The RTR hardware system allows the humanoid to learn safely, but sample efficiency is still a huge problem for real-world learning. To address this, we propose a novel algorithm to boost learning efficiency. Our approach uses a dynamics latent to steer the policy's behavior in the real world. It consists of 2 stages of simulation pre-training and 1 stage of real-world learning. In the first stage, we follow a standard domain randomization pipeline to train a latent condition policy in simulation. The domain randomization parameters, like friction, damping, and armature for different environments, are encoded into a dynamics latent, which stores the environment's information. This latent is then processed by film layers to alter the intermediate features of the actor network, injecting the environment information into the policy. In the second stage, we freeze all network parameters and optimize a single universal latent. This latent is initialized from the average of all the dynamics latents from stage 1 and is optimized via PPO across all the simulation environments. With this universal latent, we enter the third stage of training. We roll out the humanoid in the real world with the help of the RTR system and perform direct PPO over the universal latent, while also training a new critic since the real-world observation space is different. With this latent optimization algorithm and the RTR hardware, we can perform real-world humanoid RL without any human intervention. We increase the humanoid's walking speed from 8 centimeters per second to 15 centimeters per second in just 20 minutes. RTR outperforms various baselines, from RMA to residual fine-tuning, in both sample efficiency and final performance by a large margin. Beyond sim-to-real adaptation, RTR can also help with real-world RL from scratch. We designed a challenging swing-up task, where the humanoid must learn to swing itself up and down. With the reward signal and a schedule of help and perturbations from the robot arm, the humanoid learned a prominent swinging behavior from scratch in less than 20 minutes. In summary, the Robot Trains Robot system highlights the importance of active force feedback and a highly efficient learning algorithm for real-world humanoid learning. The system could also be extended to train full-scale humanoids using a larger active gantry system.